Hey there, everybody. Miss Rector here. Time to review for the final. Final exams go all the way back to the beginning of this semester, so we need to remember things that we did way back when. So, each day you're going to have a video like this. Today is about the math that we learned about at the start of the year. So, taking measurements, working with significant figures, converting things, scientific method, all that early stuff. So, in front of you, when you watch this or any of these videos, every day I would show up with a periodic table, calculator, pen and paper, do some practice. Okay. So, let's start off with a little bit of taking measurements here and calculating density. So, this is, of course, a graduated cylinder, and one of the ways we might get the volume of an irregularly shaped object like this is we might use water displacement. So, started with a initial water level here, and then we put the item in the water goes up. Eureka, we've got the volume, right? We can figure out the volume of that thing that we put in the water by taking the final minus the initial. So let's talk about the measurements that we're going to take here. First of all, to read, there's usually a little bit more pronounced meniscus, that little dip that water does, and you read at the bottom of the meniscus. In this particular picture, we'll just say we're going to read the bottom of this line. Now, here's the 15 mark, here's the 16 mark, here's the 17 mark. So we know but it's not on that line, so it's more than 17. This is where that estimated digit comes in. So every time you take a measurement, if it was right on the line, I would say it was 17.0, but it's not. It's not 17.0, and I need to let the person who is looking at my data understand that it was not exactly 17 milliliters. It was a little bit more. But this instrument doesn't have any more lines, so I have to estimate where it is. So for me, it's not halfway there, so it's going to be less than less than 0.5. So I'm going to say it's 17.1 milliliters. Now, you might have said, I would have said 17.2. That's okay, because everybody in science knows that that last digit is an estimated digit. So we all know to take it with a little bit of a grain of salt. Like, oh, if they put 17.1, I might have thought it was 17.2. This is an estimated digit. So even if you never see this, you know from this that it was more than 17, but less than 17 and a half, right? Or somebody wouldn't have put that. So these are all significant measured numbers, right? Now, on this one, when we look at the final, it's not quite the 20, but it's definitely more than 19. So again, maybe you would say 19.9, but I put 19.8. That's okay. So if you had said 17.2 and 19.8, you're going to get a different measurement for the volume of this piece of rock. So we are always limited in any math that we do by our sensitivity of the instrument, let's say. So for this one, if I want to find out the volume of the rock, I'm going to take final minus initial. So let me get my pen here. Oh, I don't have my pen on. Okay. So if I take, now remember, when you're adding and subtracting for significant figures, you're going to line up the decimals. So that's terrible. 19.8 minus 17.1 is going to give me 2.7 milliliters. That is the volume of this rock. If I want to find density, I need a formula for that. So I need to know the density, I'm just going to write it here, is equal to mass divided by volume. So I've got the volume here, and they told me the mass right here. Boop, boop, boop. Notice how many more significant figures. They must have had a really sensitive balance when they got this mass. But I didn't have a very sensitive instrument when I measured the volume. So that's going to limit my answer. So when I do the math, and I take the mass, the 51.842 grams, well, can't go that far, and divide it by 7, I'm not good today, 2.7 milliliters. When I put that in my calculator is going to give me this big long number, like 19.2007. Sorry, trying to look and do this. 074. Okay, but that's a lot of significant figures that I can't use because this piece of data that I used only has 2 significant figures. And when you're multiplying and dividing, that means my answer is limited to the number with the least amount of significant figures. So since this one only has 2, my answer can only have 2. So I have to drop all of this stuff and just say 19, and that is grams per milliliter. Or, of course, that could be grams per centimeter cubed, since you know a centimeter cubed is the same thing as a milliliter. So here we've covered how to take a measurement, what an estimated digit is, significant figures, how to multiply with them, and how they limit you. When we add and subtract, we just line up the decimals, and you can't go any further than the least amount of decimal places. And then, of course, our calculating our density. So that's a lot of stuff already from first chapter. We also learned how to convert within the metric system. So we learned all these different prefixes. So we have base units in the metric system, like a gram, a second, a meter, a liter, all these basic units. And then the metric system just uses multiples of 10 and adds prefixes. So if I have 10 grams, that's a decameter. If I have 100 grams, it's a hectometer. If I have 1,000 grams, did I say? If I have 1,000 grams, that's a kilogram. I don't know why I said meters and grams there, sorry. But if I have 1/10 of a gram, that's a decigram. 1/100th of a gram is a centigram. 1/1000th of a gram is a milligram. So what prefix you use depends on what kind of thing you're measuring. It's the same in our American system. If you said, well, how far away is Cincinnati from here? And I said, oh, it's like 6 million inches. That wouldn't make sense to you. We have a hard time wrapping our head around these big numbers. So I would give it to you in miles. I'd say, oh, it's like 100 miles, right? So same with this. If I said, how far is Cincinnati? It wouldn't make sense to give it to you in meters. I would use something like kilometers. So if we take any number, let's just say, oh, I don't know. Can I make up a number here? 4,256 meters. And I want to turn that into kilometers. Okay, so meters, just an M by itself, means it's a base unit meter. And I want to go to kilometers. Then I need to go 1, 2, 3 steps to the left. So I move my decimal 3 steps to the left. So if there's no decimal there, you assume it was here. And you'd go 1, 2, 3, dividing by 10 3 different times. So I would get 4.256 kilometers. If I wanted to take the same meters and turn it into, let's say, millimeters. So 2 small m's means the first one is milli and the second's a meter. So again, I would start with my starting number and I'd move it 1, 2, 3 places, but this time to the right. So I would have started here and gone 1, 2, 3 places and had to fill in zeros. So it would have been 4, 2, 5, 6, 0, 0, 0 millimeters. And again, 4 million, it's a hard number to wrap your head around. So that's why we're going to use things like scientific notation in science. So remember, you're going to need to convert within the metric system. You should be able to at least know these. Of course, there's many more. There's after, if you kept going, you'd find micro and nano and pico, and up here you'd have, further up you'd have giga and tera, and carrying on up that direction. So, but if you know just these basics, so some people like King Henry died by drinking chocolate milk as a little anagram to remember it. I prefer that kittens hate dogs because dogs can't meow. That's just me. So, whatever you need to do to remember that, keep it in your head and be able to go back and forth at least within the basic metric prefixes. So we said we don't like really big and really small numbers in science. We have a way to write them with scientific notation. This is where your scientific calculator will come in really handy too. So first of all, let's remember the rules for scientific notation. There should be a number here that is bigger than 1 and less than 10. Then you have times 10 to some power. So those are the basic parts of a number in scientific notation. So how do we get there? If you take this as the original number, okay, and you said, I want to make a number that's bigger than 1 than less than 10, where would I move the decimal? You'd move the decimal over here, right? So you'd have 2. To get that decimal to move, I had to move it how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So that becomes your power of 10. So times 10 to the 9th. Now, the negative versus a positive here. The negative number means your original number was less than 1. So you moved it 9 spaces and it was a number less than 1, right? So negative 9. So I'm going to write another one here. Let me write out the number and you try to write it in scientific notation. So 2, 4, 3, 0, 0, 0. So pause the video, take a second, try to do it yourself. Now I'll go ahead and do it. So I want a number that's bigger than 1, less than 10. So I want my decimal right here. 2.43 would do that. Still on vacation, I guess. And then you'd have your times 10, and your power would be how many places you moved it. So I moved it from here, 1, 2, 3, 4, 5 spots. Since that original number was bigger than 1, that's a positive 5. Okay, I'm going to write another one. You pause and try to do it. So 0.0023. So pause the video, try it yourself. Now, I want a number that's bigger than 1 and less than 10. So I'm going to want that decimal right here, 2.3. I had to move it over 1, 2, 3 spaces. So times 10 to the third, and that was a number less than 1, so that's the negative third. Okay, let's try going the other direction. Let me erase some stuff here. It's my eraser, right? Yeah. Okay, let's go the other direction. Let's say I give you a number in scientific notation, like 2.1 times 10 to the 4th. And you have to write it the other way. Well, I know it's going to be a number bigger than 1 because this is positive. So I'm going to move the decimal 4 places. And to make it bigger than 1, I'm going to move it this direction. So 2, 1. So I get 1 place to get it past there. And then 3 zeros after that. So I moved it 1, 2, 3, 4 places. Right? Good. You try this one. 3.2. So I'm going to take the decimal and move it 3 times. Since it's negative, I want a number that's smaller than 1, so I'm going to move it to the left. So it'll move 1, 2, 3 spaces, and I'll have 0.0032. Okay, let's talk about the math. This is where having a scientific calculator would be wonderful for you. If you don't have one, you can still do it. It's just a much bigger pain in the butt. So let's take a look, see what we do. So let's say, back to pen, I have a number like 4.8 times 10 to the 20th power. And I want to divide that by 2.1 times 10 to the 4th power. Okay. Now, if you have a scientific calculator, you can just type these numbers in. Now, somewhere on your calculator, there's a special button. It might be 2 capital E's like this, or EXP, or it might be like some of them have times 10 to the nth power or something like that. So for those, you're just going to type the number in here, hit whatever button this is. So on my calculator, it's EE. So I do not type times or 10, right? I just type EE, and then I put the power in, 20. Then I hit divide, type 2.1, EE, and then the 4 for the power. And then it gives me an answer. Now, if you are doing this the hard way, you have to break it apart into 2 pieces. If you only have a 4-function calculator, you can say, well, let me start with 4.8 divided by 2.1. So 4.8 divided by 2.1, and I get 2.28 and a bunch of other numbers, but I know I'm limited to 2 significant figures here, so I'm going to say that's 2.3. And then times 10. Now, if I was multiplying, I would add the powers. Since I'm dividing, I'm going to subtract the powers, so times 10 to the 16th. Now, try this math on your calculator. Make sure you get the same answer that I got here. If not, let me know if you're having troubles using your calculator. All right, so scientific notation, and then we talked about significant figures. So again, when you take a measurement like this one, we know the 18 is right, we know the 7 is right, and then the last digit is our estimated digit. So they're all significant figures. So when we do the math, we have to know how many significant figures something has. So if you haven't understood what I've been saying when I say significant figures, here's your lesson on what figures are significant. The best rule is the Atlantic Pacific rule. So here's a map of the US, right? Over here we've got the Pacific. Over here we've got the Atlantic. All right, so if you're given a number like 2050000, and we want to know, okay, how many of these numbers are significant and which ones are, that means which ones are important, do I have to keep, and which ones could I drop, like if I was writing this in scientific notation. So any number that's not a 0, definitely significant. It was measured and written there for a reason. But some zeros are just placeholders. So how do we know the difference? A sandwiched 0 like this is a real measured number, but trailing and leading zeros can give us trouble. So use the Atlantic Pacific rule. If a decimal is present, you come in from the Pacific side. If a decimal is absent, you come in from the Atlantic side. So here there's no decimal, so the decimal's absent. So I come in from the Atlantic side and I can skip any zeros, but as soon as I hit a real number, everything after that is significant. So this has 3 significant figures. Let's say I'd written it like this, 0.00000205. Okay, so this has a decimal as present. So I come in from the Pacific side. I can skip all the leading zeros, but as soon as I hit a number, all those are significant. If there was another 0 out here, it would be significant because that 0 would be a measured 0. You wouldn't write it unless you'd measured it, right? So That is how you can tell the number of significant figures something has. All right, we did converting within the metric system, but then you also need to be able to convert things that aren't necessarily in the metric system. So, for example, I gave you something at the beginning of the thing. Let's see, I said, how far is it from here to Cincinnati? I said, oh, it's about 100 miles. Notice I said about 100, so there's only one significant figure there, right? If it was exactly 100, I'd say it's exactly 100 miles, and I'd put a decimal there, and then we'd have three significant figures. So let's say it's exactly 100 miles, because it pretty much is. I think it's 99.5, so depending on whose house you're going to, you would have maybe exactly 100 miles to go. So if I wanted to figure out, okay, how many inches is that? Then I need to do some converting. And I don't happen to know how many inches are in a mile, so it might take me a couple of steps. So we use dimensional analysis. Okay, draw a cross, put whatever you're given in the top left with the units. So here I've got 100 miles is what I'm given. Now I need some kind of conversion factor. And again, I don't know how many inches are in a mile, but I do know that 1 mile is equal to 5,280 feet, which is totally random, unlike the metric system where everything's nice numbers and multiples of 10. But anyway, here we go. So I put the thing, this conversion factor has two halves. One half's going to go on the top, one half's going to go on the bottom. And whatever unit you want to cancel, that's what units right here needs to go on the bottom. So my 1 mile is going to go down here, and my 5,280 feet is going to go up here. Okay. Now, if I wanted feet, I would stop right here and just multiply 100 times 5,280 and get 528,000. But I want inches, so I need another conversion factor, and I know that there's 12 inches in 1 foot. And you might say, well, am I being, what about this one here? Is that going to limit me on my significant figures? No, because this is the conversion factor, so it's exactly 1 mile. I could just as easily write 1.000 miles is equal to that many feet, in which case those are significant zeros. So anyway, to get from feet to inches, now I want my feet term on the bottom. 1 foot is 12 inches. So when I put that in my calculator, I'm going to multiply across, divide down. So 100 times 5,280 divided by 1 times 12 divided by 1. Let's see, my calculator gives me 6,336,000 inches. Now, if I had just said it's not really 100, it's just around 100, then I can only have one significant figure. If I say it's exactly 100 with this decimal, then I can have three significant figures, which means I can keep these three, but I got to round. So I'd have to write 6, 3, this would become a 4 because I'd have to round it up, and then 0, 0, 0, 0. So if again, I was like, it's around 100 miles, then I could only say, oh, it's around 6 million inches because I could only be that precise in my measurements. Okay, so that's dimensional analysis, how to convert anything. Draw your cross, put what you're given in the top left, get your conversion factor, put the thing you want to cancel on the bottom, the thing you want on the top, multiply across, divide down. And then, of course, we talked about scientific method and how it's never really a straight line. It's this ongoing process of learning more and changing your ideas based on your data. So, of course, we start by making observations. Hey, what's going on here? What did I see? Think of interesting questions. Formulate a hypothesis. What do we think is happening? Now, this is the key step. You have to develop testable predictions, right? So it has to be something you can test. Then when you run the tests, gather the data, figure out what happens in the tests, you might develop a theory from that. It might support what you thought in your original hypothesis, and you get to come up with a theory. Or it might not support what you thought in your hypothesis. You might have to refine things, go back, reject that hypothesis, come up with a new one, and find new ways to test that too. So, you know, a lot of things in science have changed over the years. When people first tried to figure out what heat was, for example, they had this caloric theory of heat. They made observations like, hey, when I put the hot mug on the desk gets hot, right? So they thought that heat was thought about, well, what is heat? They came up with the hypothesis, okay, heat is like a fluid that flows from one thing to the other, which matched some tests, like the hot mug on the desk making the desk warm. But then some smart spark said, but wait a minute, what if I rub two cold things together and they get hot? That's not flowing in from anywhere. So that didn't agree with the hypothesis, and they had to go back and change it. That's why now we have the kinetic theory of heat, which involves like particle motion, and the temperature is all about measuring the energy and the movement of those particles. So that hypothesis has been supported by many, many, many different tests over and over. But the minute somebody tests something and proves it wrong, well, that's out. And we have to, come up with a new theory. So now we have the kinetic theory of energy. So I think that's enough for today. Go ahead and make sure if you have any questions, you know how to reach me. And there you go. Get ready for that test.